All right, hello. So I'm going to talk a little bit about these processes that are called adiabatic processes. And so in the picture, what's shown is an adiabatic compression of a gas. And what that means is that the gas is in a cylinder, but the cylinder is very well insulated from its environment. So you have something like styrofoam all around the cylinder. And so the effect of that is that no heat flows in or out of the gas. So an adiabatic process is the one where Q is equal to 0. And so what we want to do here is understand what is the relationship, say, between pressure and volume for an adiabatic process. What does it look like on the PV graph? And it's a little bit more complicated than the other processes that we've considered. And the reason is that in an adiabatic process, temperature, pressure, and volume, they're all changing. And so even though the ideal gas law gives us some relation between those three quantities, we have that PV equals nRT, it's not enough to tell us like what is the relation just between pressure and volume, or just between pressure and temperature, or between volume and pressure and temperature. Okay. So to understand that, we're going to have to use the defining property of the adiabatic process, which is that Q is equal to 0. And so what that will tell us is that the change in internal energy of the gas, using the first law of thermodynamics, is going to be directly related to the work. Okay. And so that kind of makes sense. If we don't have any heat flowing in or out, then the only way that we're transferring energy to or from the environment is through mechanical processes, through work. Okay. So what we can do is take this equation and actually convert it into something that will tell us a relationship between volume and temperature. And then once we have that relationship, we can use the ideal gas law to get any of the other relationships that we want. Okay, so how do we do that? Well, the change in internal energy, of course, is related to the change in temperature in the usual way. So that's NCV delta T. And what I want to do is I'm going to assume that we're talking about just a very small change in, say, the volume of the system. So let's say we're talking about actually an infinitesimal change, where maybe the volume gets a little bit smaller, the temperature gets a little bit higher, the pressure changes a little bit. And the reason why I want to make it infinitesimal is that that's the only place where I have a nice expression for the work that doesn't involve an integral. Okay, so if we have an infinitesimal change, then I can write the work as P times the infinitesimal change in volume. Okay. And so now this is a relationship between the temperature change and the volume change. It also has the pressure there, but what I'm going to do is use the ideal gas law to eliminate that. So P is equal to nRT over V. If I make that substitution, then I have an equation that just involves T and V. So let's do that. We get NCV dt equals minus nRT over V dV. Okay, and now we can simplify things a little bit because the n's cancel off on both sides. And I'm going to divide both equations by t so that we end up with CV times dt over t plus r times dv over v equals to 0. Okay, so now this equation, it's actually common to simplify it a little bit more, and let's divide by CV. And so what I'm going to do is write that as dt over t plus r over CV dv over v equals 0. And now what usually people do is to remember that the Cp was equal to Cv plus R. And so we can write R equals Cp minus Cv. And so R over Cv is equal to Cp over Cv minus 1. And then that ratio, Cp over Cv, is what people usually refer to as the Greek letter gamma. Okay, so this is just the way people normally write this relationship is in terms of gamma, but it makes just as much sense in terms of the other constants as well. Okay, so this is all equivalent to saying that dt by d divided by t, the fractional change in temperature, plus gamma minus 1 times the fractional change in volume is equal to 0. Okay, so now in the textbook, they basically take that and say, okay, let's just integrate the whole thing, and they get some logarithms and they rearrange that. You can see that derivation in section 19.8. But what I want to do is a little bit more qualitative and just first kind of convince you that this equation right here is enough to give us a relationship between temperature and volume. And then I'll tell you the answer and just show that that must be the right answer. Okay. So first of all, if we have an equation like this, basically, if I tell you the change in volume, then you can use this equation to figure out how much the temperature changes. Okay, assuming we know what the temperature and the volume are presently. Okay, and so then you could just keep using this equation. If I had a larger change in volume, I could just keep using that. Do a small change in volume, figure out how much the temperature changes, adjust the volume of the temperature, and then do it again. Figure out if I have a little bit more change in volume, how much does the temperature change? Okay, and so this should be giving us the relationship. This equation is enough to tell us what is the relationship between temperature and volume. And so now if we find some relationship between temperature and volume that actually satisfies this, we'll know that we have the right answer. Okay. So let me just write down the answer then. The answer that turns out to be equivalent to that is this power relationship that T times V to the power gamma minus 1 is a constant. Okay, so let's see how we can show that this is sort of equivalent to that expression involving the infinitesimal changes. Okay, and we're going to use a little bit of calculus here. So I'm going to make use of some things that you've been learning hopefully in math. And so I want to imagine that T and V are both functions of time, that we're changing the system, so volume changes with time, temperature changes with time. And so if I think of both of those as functions of time, then the whole thing says that some function of time is a constant. Okay, now if I differentiate that with respect to time, I should get 0. Okay, so 0 should equal d by dt of t times v to the gamma minus 1. And now I'm going to use the product rule. So that says that that derivative is dt by dt times v to the gamma minus 1 plus t times d by dt of v to the gamma minus 1. And then for that last term, I need to use the chain rule. And so the derivative of v to the gamma minus 1 is gamma minus 1 v to the gamma minus 2 dv by dt. Okay, and then all that's equal to 0. Okay, so now what I'm going to do is just divide all of that. To simplify this, it turns out if I divide by my original expression, divide by t v to the gamma minus 1, then everything looks a lot simpler. So I get 0 equals 1 over t dt by dt plus gamma minus 1 dv by dt times 1 over v. Okay, and now that almost looks like what we have up here. And all I have to do now is just multiply through by this infinitesimal change in time dt. Okay, so we've got an equation now that relates the rates of change to these of volume and temperature. And if I multiply through by the infinitesimal amount of time dt to figure out how much does the volume change compared to the temperature change in that time dt, then what I get is that 1 over t times dt is equal to, plus gamma minus 1 times dv over v is equal to 0. And so that was the relationship that we derived above based on the first law of thermodynamics and the constraint that Q was equal to 0. Okay, so just as a quick review, what we did was we started with this, which is the defining property of an adiabatic process. We used that in the first law of thermodynamics to end up getting this relationship between the change in energy and the work. And then we related the change in energy to the change in temperature, the work to the change in volume. And after various manipulations, that turned into this equation here that relates the fractional change in temperature to the fractional change in volume. Okay. We understood that that was enough to determine the relationship between temperature and volume, and then we checked that this relationship between temperature and volume satisfies that equation. And so now hopefully we're convinced that for an adiabatic process, T times V to the gamma minus 1 is going to be a constant. Okay. And from that, you can now use the ideal gas law. So the ideal gas law tells you that PV over T is a constant. Okay, and then you can combine those two, and if you want T, and so you can look at that in section 19.8 in the textbook if you want to see a more detailed derivation. So that gives us PV to the gamma equals constant if we use those two things to eliminate T. Okay. And so that actually allows us to plot the adiabatic process on this PV diagram. And so it looks something like the constant temperature process, but it's actually a little bit, it actually goes to zero pressure a little bit faster as you increase volume because this gamma is greater than 1. All right, so I think that's all I have to say.